Hello everyone, welcome back to the channel. In this video, we are going to simulate Cmos inverter using ngSpice. A Cmos inverter, which is complementary metal oxide semiconductor inverter, is the most fundamental logical gate in digital electronics. It performs the basic NOT operation, producing an output that is the logical opposite of its input. So basically, a Cmos network is made up of PMOS transistor and a NMOS transistor. PMOS transistor is used as the pull-up network and NMOS transistor is used as the pull-down network. Coming to the working of CMOS inverter, so you can see here in the diagram, here PMOS is connected and this is the NMOS. Drain of the PMOS is connected to the drain of the NMOS. Both the gates are connected together and it is given to the input. From the drain, the output is taken. Source and substrate of the PMOS is connected to VDD and source and substrate of the NMOS is connected to ground. In the first case, when the input is 0, so when the input is 0, the NMOS will be off and PMOS will be conducting. Due to this, the output will be pulled up to VDD. So when we are giving input as 0, low, the output will be high. In the second case, when the input is 1, PMOS will be off and NMOS will be on. So here it will be open circuit and due to that the output will be pulled down to the ground. So output will be low. So when we are giving input as high, our output will be low. So next we'll see the graphs that we'll simulate in ngSpice. First one what we'll see is VTC, which is voltage transfer characteristics of CMOS inverter. That basically shows the relationship between input and output voltages. And second is the transient analysis that studies how the output voltage of CMOS inverter responds over time to the changing input. So these two graphs will be simulating in ngSpice. So let's start writing a code in ngSpice. So this is the circuit diagram. Here we have PMOS. This is the NMOS. Source and substrate is connected to VDD. Gate of PMOS and NMOS is given to the input Vin. Drain of NMOS and PMOS is given to the Vout. So I have marked all the nodes here. Ground is given 0. VDD is 1. Output is given as 2 and input here is 3. So first line will be the title line. Let's give CMOS DC. Next, let's define VDD, which is connected between node 1 and 0. And let's say VDD is 5 volts. Next, we'll define Vin, which is connected between 3 and 0. And let's say the value is 1 volts. Next, define the MOSFET M1. So when we are defining here MOSFET, it will be drain, gate, source and substrate. So drain is connected to 2. Gate is connected to 3. Source and substrate is connected to 1. And name of the model, let's give as PFET. Next, defining the second MOSFET M2. The drain of the second MOSFET is connected to 2 here. Gate is connected to 3. And source and substrate is connected to 0. So it will be 2, 3, 0, 0. Name of the model, let's say NFET. Next, we are defining the model. NFET is NMOS. Okay, and second model we have here is PFET, which is PMOS. Next, define the dot DC for DC analysis. So let's say Vn is going from 0 to 5 in steps of 0.1. Then control Then we have run, plot. We are plotting the output. So output is at node 2, ending the control section, and C, and ending the netlist dot end. So we'll simulate this code. I'm copying this code in text document. All the steps I have shown in the previous videos. You can check them out. Let's save this code as Cmos DC with extension SP. So now let's run this code from the console. Cmos DC.sp. You can see this graph of DC analysis. Now if I want to make the background white, then I can add one line in the code. Let's do that modification. So under control, I'll have to add a line, set color zero is for background equal to white. Save this and run in the console. See, now the background is white. Next we'll write the code for a transient analysis. So two things will change here. One is we are giving the pulse at the input, and second we'll see the transient analysis. First we'll give the pulse here for V in. Pulse in the bracket, initial voltage 0, high level voltage 5. Then we have time delay, which will keep 0, rise time 0, fall time let's keep 0, pulse width let's give 5 micro, and period of the pulse let's say 10 micro. Okay. Second change we need to make here is the transient analysis. So dot trans, I'm having here time from 0 to 100 micro in the steps of 1 micro, 0.1 micro. So in the steps of 0.1 micro, time is going till 100 micro. Other things will remain same. One more change here we have to do is we have to add input and output. So our input is at 3 and output is at 2. So input is at 3 and output is at 2. Okay. Let's save this and run this again in the console. Now both the waveforms are overlapped. Okay, so let's take one waveform on top like the last time's video. So I'll add here +6 and run the code again. Now you can see here this is the input green color and this is the output. So if you see the waveform, the input is inverted at the output. If it is 1 here, this is 0. This is 0, here it is 1. So that's it for today. If you found this video helpful, then don't forget to like, share and subscribe. Also, if you have any queries or suggestions for future videos, then let me know in comment section. Thank you for watching.